Welcome back. Today we're going to talk about singly and doubly linked lists, one of the most useful data structures out there. This is part 1 of 2. In the second part we will be looking at some source code on how to implement a doubly linked list. So for today's outline, in the first section we're going to answer some basic questions concerning singly and doubly linked lists, namely what are they and where are they used. Next, we'll cover some terminology concerning linked lists so everyone knows what I mean when I say the head of the linked list versus the tail of the linked list. Then last in the discussion, we'll talk about the pros and cons of using singly and doubly linked lists. Then how to insert and remove elements from both singly and doubly linked lists, as well as some source code. So stay tuned. Alright, discussion. So what is a linked list? Linked list is a sequential list of nodes that hold data which point to other nodes also containing data. So below is an example of a singly linked list containing some arbitrary data. Notice that every node has a pointer to the next node. Also notice that the last node points to null, meaning that there are no more nodes at this point. The last node always has a null reference to the next node. For simplicity, I will omit this in the following slides. Okay, so where are linked lists used? One of the places they get used the most is actually in the abstract data type implementation of lists, stacks, and queues because of their great time complexity for adding and removing elements. You also see linked lists in things like circular lists, making the pointer of the last node point to the first node. So circular linked lists are used to model repeating event cycles, maybe like having a round-robin ordering on a bunch of elements or representing corners of a polygon. So definitely a lot of uses there. Linked lists can also be used to model real-world objects, such as a line of train carts. That could be useful. And moving on to some more advanced examples, we also heavily use linked lists in hash table separate chaining and for adjacency lists and graphs. We'll get to those in a later video. Okay, a bit of terminology surrounding linked lists. First thing you need to know when creating a linked list is that we always maintain a reference to the head of the linked list. This is because we need somewhere to start when traversing our list. We give a name to the last element of the linked list also. This is called the tail of the list. Then there are also the nodes themselves, which contain pointers. Pointers are also sometimes called references, and these pointers always point to the next node. You should also know that the nodes themselves are usually represented as structs or classes when actually implemented. We'll get to this when we look at the source code. Okay, singly versus doubly linked lists. So concerning the kinds of linked lists that there are two types, singly linked and doubly linked. Singly linked lists only contain a pointer to the next node, while doubly linked lists not only contain a pointer to the next node, but also to the previous node, which makes it quite useful sometimes. This is not to say we cannot have triply or quadruply linked lists, I just wouldn't know where to place the additional pointers. Pros and cons of doubly linked lists. So there are trade-offs between picking a singly and a doubly linked list. What are they? If we look at the singly linked list, we observe that it uses less memory. Why? Well, pointers to nodes can actually take up a lot of memory. If you're running on a 64-bit machine, references use 8 bytes. On a 32-bit machine, 4 bytes each. So having a singly linked list means you only need one pointer for each node, hence twice as much memory is saved. A downside, however, is that you cannot access previous elements because you don't have access to them. You would need to traverse from the head of the linked list all the way up to the previous node to find it. Now concerning doubly linked lists, well, a great pro is that having access to the tail, we can easily traverse the list backwards, something we can't do with a singly linked list. Also, having a reference to a node you want to remove, you can remove it in constant time and patch the hole you just created, because you have, again, access to both the previous and the next nodes. This is something you cannot do with a singly linked list. You would leave the list severed in two. A downside, however, to the doubly linked list is it does use up twice as much memory. Okay, let's go into some implementation details on how we can create linked lists and remove elements from linked lists. Starting with singly linked lists. So here is a singly linked list. I've outlined where the head and the tail is. Now we want to insert 11 at the third position where 7 is currently. Let's walk through an example. So the first thing we do is we create a new pointer which points to the head. This is almost always the first step in all linked list operations. Now what we're going to do is seek up to, but not including, the node we want to remove. So if we seek ahead, we advance our traversor pointer, setting it equal to 5's next node, which is now 23. And now we're actually already where we need to be to insert the next node. So we create the next node, that's the green node, 11. And we make 11's next pointer point to 7. And the next step is to change 23's next pointer to be 11. Remember, we have access to 23's next pointer because we have a reference to it with the traversor. Okay, and now if we flatten out the list, we can see that we've correctly inserted 11 at the right position. And we're done. Okay, alright, time to insert with a doubly linked list. This is much trickier because of all the pointers flying around, but it's the exact same concept. Notice that the doubly linked list not only has pointers to the next node, but also to the previous node. We also have to change those in the insertion phase. Okay, create a traversor pointer which points to where the head is and advance it until you are just before the insertion position. So we advance the traversor by 1 and now we're just before the node, so we stop traversing. Let's create the new node, which is node 11. Point 11's next pointer to equal 7. Also point 11's previous pointer to be 23, which we have a handle on because of the traversor. Now we make 7's previous pointer equal to 11, so we can go backwards from 7 to 11. And the last step, make 23's next pointer equal to 11. This is so that we can go forwards from 23 to 11. So in total, remark that we changed exactly 4 pointers. So if we flatten out the list, you can see that 11 has been inserted in the correct position. Alright, now how to remove elements from a singly linked list. So suppose we want to remove the node with a value 9. How do we do this? Well, the trick we're going to use is not to use one pointer, but 2. You can use one, but for visual effects it's easier to show you how it is done by using 2. So we create pointers trav1 and trav2 for traversor 1 and traversor 2 respectively. So traversor 1 points to the head. Traversor 2 points to the head's next node. Now what we're going to do is advance trav2 until we find the node we want to remove, while also advancing trav1. Okay, we have found node 9, so this is the stopping point. I'm going to create another pointer to the node we wish to remove, so we can deallocate its memory later. Okay, so now I had to have advanced trav2 to the next node. and node 9 has turned red. I've done this to indicate that at this point, node 9 is ready to be removed. I'm just keeping it around for the visual effect. Okay, so now set trav1's next pointer to be equal to trav2. And now it is an appropriate time to remove the temporary pointer because we're doing nothing with it. And there, temp has been deallocated. Make sure you always clean up your memory to avoid memory leaks. This is especially important in C and C++ and other programming languages where you manage your memory. Now you can see that 9 is gone and our singly linked list is shorter. Okay, now for the last bit of implementation, let's look at how to remove nodes from a doubly linked list, which is actually easier in my opinion to removing from singly linked lists. The idea is the same. We seek up to the node we wish to remove, but this time we only need one pointer. One traverser pointer, because each node in the singly linked list has a reference to the last node, so we don't need to manually maintain it like we did with the singly linked list. So let's start trav at the very beginning and seek until we hit 9. Okay, we've reached 9, and we want to remove it from the list. To do this, set 4's pointer to be equal to 15. We have access to 4 and 15 because they are trav's previous and next pointer, respectively. Similarly, set 15's previous pointer to equal 4. Notice that trav is now red, meaning it is ready to be removed. So we get rid of trav, and now if we flatten out the doubly linked list, we see that it no longer contains 9. Let's do a bit of complexity analysis on linked lists. How good actually are linked lists? On the left column, we have singly linked lists, and on the right, doubly linked lists. The complexity for searching in a linked list is linear in the worst case, because if the element we're looking for is not there, we have to traverse all of the n elements. Inserting at the head, though, is constant time, because we always maintain a pointer to the head for a linked list, and hence we can add it in constant time. Similarly for the tail. To remove the head of a singly linked list and a doubly linked list is also constant time. Again, because we have a reference to it, so we can just remove it and advance the head by 1. However, removing from the tail is another story. It takes linear time to remove elements from a singly linked list. Can you think of why? Well, even if we do have a reference to the tail in a singly linked list, we can remove it, but only once, because we can't reset the value of what the tail is. So we had to seek to the end of the list and find out what the new tail is equal to. Doubly linked lists, however, do not have this problem, since they have a pointer to the previous node, so we can continually remove nodes from the tail. And finally, removing somewhere in the middle is also linear time, because in the worst case, we would need to seek through n-1 elements, which is linear. Alright, time to have a look at some source code. I have implemented a doubly linked list. We can have a look at it in some detail. Also, if you want the source code for the doubly linked lists in the next video, have a look at the code repo provided below. It contains all the data structures I will be covering in this series. Guys, thanks for watching. I will see you in the next video.